Okay, so welcome everybody to this breakout session. This breakout session is virtual validation for automated vehicles. So just going to start with a little bit of housekeeping and a brief introduction, really. And the main part of the presentation will be from Jackie. So this will take, in terms of the presentation itself, about 35 minutes. So we were going to have a little bit of time for a short Q&A at the end. If people are prepared to stay a little bit longer, we can still do that. That would be great. So please submit your questions in the chat and we will try and cover them at the end. If we don't get time to do that, then please contact info@smartmobility.london and we can get in touch through that. So my name is David. I'm Chief Scientist for Safety and Investigations, so one of 3 Chief Scientists at TRL. And I'll do a little bit of an introduction and then we'll get into the meat of the presentation, which will be from Jackie, who's our CAVBIM consultant. So hopefully you can hear me okay. I'm just going to check on the chat to make sure there's nobody saying they can't hear me, which seems to be the case. Okay, so a little bit of introduction. Most of the work that we're going to talk about here was actually done under the Streetwise project. So I'll give a little bit of background to the Streetwise project just to put this work in its original context. We are taking this work forward in several current projects, so we'll maybe touch on that in the Q&A at the end. So what was Streetwise? Streetwise was an Innovate UK project to develop a trial of urban autonomy for commuters. So it looked at quite a wide range of issues. So things like how would you integrate an automated service into existing public transport? How would you do that without cannibalizing, for instance, the tube network or the bus network? How would you insure an automated vehicle, or how would you insure a service provided by a fleet of automated vehicles? How would you understand the level of safety so that you can understand the risk and provide the insurance support for that kind of service? We looked at things like what is the public perception of safety of an automated vehicle and the services provided using an automated vehicle. And we looked at certification. So what are the things you might want to do to show that an automated vehicle is safe, either at the sort of UN or European level, UK level, whatever that might be. So that's the main thing that we'll be talking about in the presentation here today. Streetwise was a 2.5-year project. It finished in February this year with a total government grant of £15 million. 5AI, now 5, was the lead of the consortium. And the other consortium partners were TRL, Transport for London, Direct Line Group, McLaren Applied Technologies, Claytex, University of Oxford, and the Warwick Manufacturing Group. So what did we do in the project? So the first work package of Streetwise was essentially the development of the vehicle platform, the sensor platform, and the automated driving system, so the core technology to automate the base vehicle. The majority of this work was 5, and the largest part of the budget really was allocated to that work. We had a second work package which looked at safety and insurance. So that was trying to answer those questions to do with how would you understand the risk and come to a decision about insuring the automated vehicle. And TRL's role in this was to develop the safety case for the on-road trials for the automated vehicle. So initially that was in a route near Millbrook Proving Ground, so between Millbrook and the nearby town of Flitwick, so out on the public road, up to 60 miles per hour speed limit, 30 miles per hour in town, with all sorts of road features. And that safety case was updated continuously on a week-by-week basis as new capabilities were added to the core technology and as new road features were brought into the trial. We had a work package that looked at service provision, so what sort of considerations would be there for licensing of a service like this? How would routes be selected to integrate with existing public transport? And at the end of the Streetwise project, we ran a trial. So over 100 people were able to experience the service on a 30-kilometre round-trip route in London. And we got information and surveys from those people before, during, and after their experience in the automated vehicle, with very, very positive feedback from people in the main. And lastly, we had a work package looking at regulation, certification and risk. So one module of that looking at developing tools to analyze the data available from an automated vehicle, and also to benchmark the performance of human drivers. And then what we're really going to be talking about here today, the independent simulations segment, which looked at things like sensor models and the development of a scenario description language. But the thing we're really going to focus on here is a tool chain that we developed at TRL to support the independent certification of an automated vehicle. So we looked at why we would want to do that, what are the elements of that tool chain, and at the end of that process, what do we do with the data that you would get from that tool chain? How do you decide at the end of the day the automated vehicle is safe enough to be put on the public road or not? So that will form the meat of the presentation. Checky, over to you, I think. So if I stop the presentation, and you should be able to share screen.
Yes, we shall try, David. We shall
Excellent.
try. I hope everyone can see my screen now. Well, I can't see you anymore because I just launched the presentation.
And it's showing just fine for me, so that's good.
Okay, I hope everyone is fine. I can't see the questions or anything, so I'm hoping everyone is with me. David, please feel free to interact as I'm talking. So once again, thank you for joining us. You have seen some little bits of what we're going to show in the video that played at the end of the main event. As David said, we're going to talk about what we have done in the Streetwise project, but the context in which we're talking about these will give you some taste of the different kind of things we tried, different assets we tied together, different processes we explored, different concepts we looked at. So please look at it from the wider perspective of what can be done in the future based on the things we're going to show you today. And let's get into it. I divided this presentation into 4 parts. The first part is just to familiarize ourselves with the problem in question we're trying to answer. So let's start with today's cars. You've seen a car like this in the video. This is a Nissan EMV 200, one which you can buy off the shelf, not off the shelf, but off the dealership today, an electric van. And for vehicles such as this, we already have regulations in place, including regulations, safety regulations for frontal and side impact test. And we also have most manufacturers carrying out voluntary impact test through Euro NCAP. We have regulations about emissions to ensure the health and well-being of public, to protect the environment. We have regulations in place relating to MOT, so that once this product is on the road for a certain amount of time, you have some sort of confidence that it's in still good and safe condition. And most importantly for our presentation today, we have regulations in place for the driver. As we all know, these drivers, we need to go through driving and theory tests to show that we understand that we can execute the necessary commands to drive a vehicle safely within the limits, obviously. And there is a hazard perception test, which is kind of an edge case preparation for those unlikely events as much as possible, obviously within the limitations of the system. And we have the system of enforcement and penalties to try and remove those people who do not behave within a safe manner. Now, what we're trying to achieve with the automated vehicle technology is obviously we are trying to remove Mr. John Smith there to a certain extent with different levels of autonomy, and we are replacing him with different kind of sensors and systems on board, which makes this vehicle from a regular ENV 200 to an automated vehicle, as you've seen in the videos. And what are these systems? These systems often include things like different types of cameras. We often have LiDAR systems on board, and we also often have radar systems, and more systems can be developed in the future as well. And usually these sensor systems replace the sensor inputs of a human being. And then this input is then put into the hardware and then to the software in the vehicle, which is making the necessary decisions to drive this vehicle in a safe manner and make some difficult decisions, probably at times. So now that we are suggesting to replace this person with all these systems, hardware, software on board, then the question becomes, how are we going to replace all these systems we put in place over years to make sure this person can do the task in a safe manner. And not only that, with automated vehicles, we are setting the bar higher. We are expecting more than that. So how are we going to ensure this vehicle can do those things? Now, obviously, as you would expect, this will involve lots and lots of types of testing in environments such as this. You have already seen in the video, this is a digital twin of the Smart Mobility Living Lab we've been developing over the years. And what we envisage is we obviously expect different levels of physical testing, starting from initial type testing in closed environment, gradually going into more challenging environments such as Smart Mobility Living Lab. But the difficulty with physical testing, yes, it will form the backbone of the assessment process. It is not very easy to experience edge cases. And by edge cases, what I mean is those cases where rare human environment and vehicle factors come together to create these one-off challenging situations. And you can drive lots of miles in an empty road, and the chances of experiencing these edge cases will be small. This is why you see a lot of large manufacturers quoting numbers in the range of billions of miles needs to be traveled in the testing environments to ensure a vehicle is validated. I believe this is to do with the likelihood of going through these edge cases. But the beauty of simulation is when we complement physical testing with simulation, we control the environment and we don't have to wait for things to happen to us. We can make things happen ourselves by using the information we gain from the world. So going into this vehicle, we know this world is dynamic. It's not just one time in the day, different times of day, different weather conditions, lots of different actors going on, lots of different variables. And what we don't want to happen is this gentleman to jump in front of our vehicle for the first time in the physical world. Ideally, if possible, we want to prepare this vehicle for such an event before we send it to the physical test as much as possible. The other question is what happens when, for example, the sun is shining right into the camera. Is probably challenging in terms of like contrast issues. Can the vehicle survive that sort of situation? Example comes to mind from recent years when there was an automated vehicle driving, automated to an extent, vehicle driving side by side to a white curtain side truck, and the position of the sun was in such a case that in the cameras the vehicle looked like the open sky, and then the vehicle decided to drive into this truck, causing an incident. Such incidents obviously happen only when certain environmental, vehicle and human factors come together. So the aim should be for us to develop the simulation capabilities as much as possible to create these challenging situations without experiencing them in real world. The other examples I can think of, when it's raining really heavily, will the systems on board still function? When it's snowing really heavily, the lines on the ground may be covered, the road signs may be covered. Will the system still function in these challenging conditions? So these are some of the questions that lead to this project. And in this project, we basically try to answer on main groups 3 questions. First, scenarios. What scenarios are relevant for this vehicle, and how can we generate a system to develop these, to generate these scenarios that keep coming and are relevant to our automated vehicle system in question. The next one is, once we decided on some of the relevant scenarios, how can we take these scenarios and put them into a simulation environment? And then we assume there will be lots and lots of iterations of any simulation on any platform, and ultimately, regardless of the platform, we will end up with lots of results. Then the question is, how are we going to interpret these results? What is going to be the definition of success? And these are the questions. We will have 3 dedicated sections on this. David?
Yeah, thank you, Czeki. So we've seen there a little bit of the background to this, some of the justification for doing the work. I think I'd also like to note that one thing that we feel is important, we expect that the approval of a vehicle would, of an automated vehicle, would fall under something like the current type approval system under the United Nations. And that will basically say that the vehicle is competent to be on the road. But the driving rules are different in every country, and the driving norms are different in every country. And of course, we drive on the wrong side of the road compared with most countries that are developing an automated vehicle. So we think there's a very strong case for having a local independent certification as an extra layer to assure the safety for our environment, our road, and our road users. So that, I think, also is an important part of the justification for this work. Okay, so I think we'll look at scenario selection.
Yes, thank you, David. Next up, let's start with the process we looked at in this project. So again, looking at the problem, we're looking at a single crash in this picture. We see in this specific incident there were 2 serious injuries, no fatalities. When I look at this picture, I immediately see the potential of the savings we can achieve through developments in these automated vehicle technologies and all sorts of different driver assistant systems. And this is just one incident. Obviously, there are lots and lots of different types of collisions happening around Great Britain every day. And when you think about it, at the least, you would expect this technology, the automated vehicles, to eliminate as much as possible the human error to an extent. Obviously, there will be different discussions about the problems they may introduce, but at the least, you would like to see, as they said on the panel discussion, you want to see some sort of improvement over the existing conditions. So when I look at this picture, I see a massive opportunity to improve things if we do this right. And looking at the Stats 19 data, Stats 19 data is the national data collection system where the data is collected on any injuries incident. And we're looking at over 1 million incidents in the last 5 years. That is a huge data to tap into, which we can, in some form or shape, try to bring into our simulation. So this is what we wanted to start with. Let's look at the general picture. But the question is, how are we going to choose which ones to bring into simulation in our small project, limited scope? So what we've done is we developed something what we call a priori dashboard. This is basically filtering incidents from the large pool into common types of incidents which are in a more manageable number. So for example, we can say the most common incident perhaps is one on T-junctions in certain conditions. The next most common is perhaps ones in rear end shunts in roundabouts and things of that nature. So what we've done is we filtered these incidents into more manageable numbers. What I want to show here now is the difficulty. Yes, there is a lot of data here, but when we want to use this data in simulation, it's not as simple as just using them. And let me try to demonstrate with this example. Now, in this case, you see we're looking at a fatal incident on a dual carriageway, a speed limit of 40 miles per hour with a single vehicle involved, which was near a junction. Now, let's try to replicate this incident in a simulation environment with the data available to us from Stats 19. Now, we know there was a single vehicle involved, and we know which direction it was traveling from the data, but the thing we do not know is which lane this vehicle was in, first lane, second lane. Also, actually, we don't even know exactly on which part of the road this vehicle was. Next is the pedestrian. We know that there was a pedestrian involved, but again, we do not know which direction it was coming from, under which circumstances it entered the road. This information is not there. This is why we needed to tap into something much more in-depth, and this is where the RAIDS comes in. For those of you who may not be aware, RAIDS is the acronym for Road Accident In-Depth Studies. And this is a program that's been funded by DFT over a decade now in different shapes and forms. Basically, there are collision investigation vehicles which attend to certain accident scenes within a certain radius to their location, and there are collision investigators on board. They go there and collect data. This database has much more in-depth data that we can tap into, and which we did in this project in a proof of concept level. So let me try to demonstrate the difference. If this is a this is a demonstration of the Stats 19 view of the world, where we know there is a vehicle, everything is a bit more blurry. This is kind of what we see from the race perspective, much more 3D. We have much more information about, for example, where the specific hardware, the infrastructure elements are, what the relevant infrastructure was for that specific incident. We know, for example, things like the distance from the edge of the carriageway in different different steps of an incident. We have much more data available about things like surface friction, temperature gradient, super elevation of that nature. We know things about different phases of the accident, like point of perception, if available, point of reaction, point of impact, things of that nature, which makes us understand this incident in much more detail. But you may ask, if this incident I'm showing here happened like this, it's a bit odd, isn't it? Like that vehicle could, the driver of that vehicle could have easily seen this person jumping on the road and should have reacted a bit earlier. And this is simply because at the moment I'm still showing you slightly from the stats 19 perspective of this incident, which is missing the single most important part for this incident. By the way, this is based on a real incident, not on this specific location, but a similar junction somewhere else, where there was a bus which created a massive blind spot for this vehicle. And when the pedestrian jumped in front of the vehicle, it was too late, because the phasing of the traffic lights in this junction was in such a way that there was a confusion. So what I'm trying to say is, if you want to understand the single most important part of this incident, we need to understand the detail. If you were throwing random cars in pedestrians without that bus in there, we're not really testing what needs to be tested in this scenario, the source of the problem. So going back to the summary of this, what I told you, we started with the national level data. We used a prior dashboard to take it into a manageable level, and then we selected some scenarios in this project. And then we enrich those scenarios, explore them further through rates data. And then we decided to then carry those ones into simulation for this project. But in reality, obviously, this is just one source of information, stats 19. In reality, there are many more sources of information for scenarios. There will be new scenarios that will be generated through the nature of these new systems they will bring with them themselves. So we're not saying this is exhaustive, but this is one of the things, as a minimum, we believe should be addressed in the simulation environment. Back to you, David.
Thank you, Jackie. So that shows the approach that was taken within the project to scenario generation, and that was tightly linked through to the work led by Warwick Manufacturing Group on the development of, or further development of, scenario description languages. So in trying to ensure that we have a common way of describing all of these conceivable scenarios. And as you said, that approach directly from real-world collision data is, I think, very important, but it is only one of the approaches that we can take there. So we are now looking at how to automate the process of identifying challenging situations and potentially near misses from the information that is available within the SMLL. So that will be added in as an extra component to this toolchain, in essence. So that gives us our scenarios, and then I think the next step is to take a look at what we do with those, how we implement those.
Thank you, David. I guess the one more thing to add to what you already said about introducing scenarios. We observe in Smart Mobility Living Lab, we already have an ongoing project where we are trying to develop these methodologies to try and automatically identify such scenarios. So that is already something that is in progress, but we will probably talk about that more later in future events. But going back to the simulation, obviously now we are at a point where we talked about one way of bringing in simulations that are relevant, scenarios that are relevant for simulation. Now the next stage is we need to have a simulation environment to put these scenarios to. Now this could be different. There are different packages available out there, but I will be talking about what we used in this specific project. But we can say that we are working with some other partners on using what we developed here in different type of simulation environments. So what you're looking at here is the point cloud, as Jonathan actually talked about in the introduction video in the main event. This is the point cloud of the Woolwich area, and actually you can see the SMLL offices here before they were SML offices. What we started with is, before the SML was even a project, there was a project called BIMCAV, Innovate UK project, where we looked at the potential benefits of using building information information modeling to support the adoption of automated connected vehicle technologies, smart mobility systems, and things like that. And as part of that project, we started developing a BIM model of certain parts of this route, and we used that model for actually planning the construction of the site. And in the later stages, we decided to continue funding this further, and we actually continued making a digital twin of the whole route. So this is what the BIM model looks like, built on top of the point cloud data. I have to also point out here that, pardon the pun, point out here that for some people, the BIM model may be more relevant. For some people, the raw data, the point cloud may be more relevant. We are showing here one tool chain, but rest assured, we have all the different forms of this data available if you need it for any other kind of purpose. And what also we invested in is we got these texturized versions of the digital twin created, and we use this, as you've seen, to create, for example, a virtual reality application, and we perceive this to be used also for like human factor trials to bring people into different type of situations and look at their input. But back to the simulation part, having this model alone is not enough for our case. For the simulation, what we also had to do, because for the simulation these are just polygons and textures and meshes, what we had to also combine this with the OpenDrive file for our simulation, which is basically an XML code describing the layout of the road, geometry of the road. Once we had these two, you can see here visualization of the OpenDrive interpretation of this model, of this environment. We could then bring these things into the simulation. Again, as you may have heard in Jonathan's speech in the main video, we used Carla open source simulation platform for this specific project, mainly because of this open source nature, and it's widely used in research communities. You can develop your own code and do things in the way you like. Here you can see we could already have third-party vehicles driving around in a representative way. To a certain extent, they can wait in like traffic calming measures for each other. They can give way to each other at junctions and things like that. Again, we are collaborating with some other simulation partners to use the base model in different packages, but that's for another day, I guess. So what I'm trying to say is we use this, but it doesn't necessarily need to be all end all solution. It's the workflow that matters for us in this project. Next, we look at an actual footage from the simulation. By the way, what you're seeing is the presentation we created in a game engine to explain the concepts a bit better. This is showing footage from the simulation before we created the texturized version. But what you see is the Ego vehicle is driving there on the left and right hand side. You see the data live coming from that vehicle that was fed into RViz. This is to show that at this point we had access to the sensors from this simulation, even though in this case the AV model was a simplified model that came with Carla. We weren't really developing an AV model in this project. It was more about creating the scenarios that AV models can tap into. But it is showing that the connectivity between the different sensors on this simulation platform was available to us at this stage. So what you can do is you can either have a simulation where your vehicle is running and doing its own thing with other actors, or you can do what we are mainly interested in this project, where you recreate the relevant incident scenarios. In this case, we used Python code to create the scenarios to control the different actors, so we can tell where the important actors were in different times of this incident, time steps. Like there was the bus, there was the main vehicle, and these were the steps of the incident, so timings of different actors. And because this is sort of parameterized, we can do iterations of this. But obviously, we do not just want to recreate that incident. We want to replace that vehicle with our own Ego vehicle, which is being tested. And this could be the whole vehicle. This could be parts of this vehicle being tested with assumptions made for different parts of the system. But the main question is, will this vehicle then behave in a way we perceive to be successful, or do we want to be in this real world scenario? And as I said, edge cases are very important, and not every edge case is created equal, let's say, because if you approach this junction from a higher vehicle, let's say, I don't know, like you would have a different viewpoint from a 8GV than on a motorcycle or from a car. So it's not necessarily the same conditions that are creating an edge case for different types of road users and different vehicles. So what we are doing is then we are creating iterations of this incident. In this case, my colleagues created over 1,000 iterations of this single scenario, whereby varying the positions, the directions, the speed of the different actors, times of the day, and things of that nature to create different iterations. And this is how we envisage that you can use one scenario and then try to find the worst possible version of it that applies to the system you're testing. Again, one way of doing it. There are many different ways of doing that. And once we have all these iterations, then we record all the results, and we end up with a massive pool of information to do some assessments with. So going back to the summary, we start with the selected scenarios, which we describe in a certain way through code. We have our simulation environment on which the vehicles can drive. We are controlling third-party actors through the Python code. This could be open scenario or other types of methodologies to control them. And then we have our input-output system available to us to connect the AV models. And we are creating results for every iteration we run. This is sort of the overview of what we envisage for this kind of process. Back to you, David.
Okay, thank you, Jackie. So that shows the very detailed implementation of the SMLL network that has been put into this model. And I think the whole network is in the model, isn't it? Something like 24 kilometers of
Yes.
route. But all of this so far shows essentially a set of tools. And for me, the really interesting bit is what we do with those tools, which is how do we explore the performance of the automated vehicle? How do we try to understand whether the performance of the automated vehicle is good enough or not good enough? And I think it's quite a nuanced discussion. So, and actually, Checky, whilst we're going along, there's a very simple question which might be easiest to answer now, which is what is the game engine that this presentation is built on?
Oh, this presentation is built with the Unity game engine, but the Carla simulation platform uses a combination of Unreal game engine and a Python client.
Perfect, thank you. Okay, and with that, if we drop into the final segment of the presentation, and actually somebody's asked if this is being recorded. Actually, each individual segment of this is available on the TRL YouTube channel. So this presentation per se, as we're doing it live at the moment, is not being recorded, but the individual segments of the presentation are available.
Also, if you're interested, we have other presentations made with game engines, so in similar areas. I don't know if you see any relevance, please contact us. We have one for the BIMCAP project I talked about earlier. But let's continue with the rest. David, if you don't have anything else to say.
That would be great, thank you.
David, is it possible if you move, where is the camera location? I can see the webinar gem screen. Are we on the top right or bottom right?
Top right, yes.
Good, because I will be showing some stuff in the bottom right now.
I moved you a couple of times to reveal things.
All right, okay, thank you. I'm glad you're watching over my presentation. Okay, so back to the question. So here we're going to show you 3 different scenarios to, again, explore some concepts. First, the orange vehicle here is, let's assume that's our ego vehicle. In this scenario, what was happening is the blue vehicle is going in back to the lane 1, and the moment it's going there, you can see it's encountering a cyclist and decides to slam the brakes. Now we're going to look at 3 different versions of this scenario. In this first scenario that's been repeating, you see that the ego vehicle is not braking harshly at all. It's using all the space available to it until the last moment. Now the question is, yes, this vehicle did not crash the vehicle in front of it, but is this what you want to see? in the brighter future, surely if there was a change in the friction of the surface there that was unexpected, that could have easily resulted in an incident. Also, personally, unless you like roller coasters much, you may not want to be in that specific vehicle in that type of behavior. So maybe that is not the best way to handle this situation. Now, going to the second one, we will see a complete opposite of this scenario, where the ego vehicle slams the brakes as harsh as possible to use all the tools in its arsenal to make sure absolute safety, but then what's happening is it's not using the available space, and it's increasing the chance of itself being rear-end shunted by another vehicle. And also, once again, probably I wouldn't want to be in that vehicle in that kind of behavior in terms of comfort. Imagine having a cup of tea in that vehicle as a passenger. Perhaps then what we need to have is a situation where the vehicle is doing the best of both worlds, using all the space available to it while being within reasonable levels of comfort. So I think then what we are trying to say with these three cases is, first off, definition of success is complicated, and it is definitely not only based on crash, no crash criteria. Perhaps it will be a complex combination of different criteria. One that in my head I think of it as is like a Venn diagram. In one side you have speed, because you want to reach from A to B in a timely manner at the end of the day. But if you do it too much, it's not safe and not comfortable. On the other part of the Venn diagram, you have safety. If you go to everywhere with 2 miles per hour, probably it will be safe, but it's not going to be fulfilling its function, and maybe it might not be comfortable if it's taking that long, the journey. On the other hand, the comfort side, if your vehicle is doing like harsh acceleration, decelerations to reach to fulfill the other parts of the diagram, maybe it's not best either. So it will be a balance between different things, I think, for these vehicle development. But going back to our situation here, what we try to do is we try to explore these success assessment criteria within our own scope in this project. Definitely there is much more to be done in this. This is nowhere near exhaustive, but it starts the conversation going, and we learned a lot by even trying to describe these criteria within our own project, opened our eyes to all sorts of different things. So what we've done in this one is, you see the vehicle again, we develop these simple areas in front of the vehicle, different zones. The first one, the red colored one, is describing an unavoidable collision zone, which means anyone going into that zone while the vehicle is traveling in that kind of speed, there will be a crash because of the physics of the situation. The next one is describing the orange part, a harsh braking zone that is avoidable, but the braking won't be pleasant. So it will be almost like a near miss. And then anything further than that, anything further than that will be green zone, which is the safe distance under which this vehicle would be expected to slow down in a timely manner. Obviously here you're seeing a simplification of the model we created because of the limitations of this platform I use for presentation. In reality, we're not looking at just straight boxes like this. We're looking at much more complex relationship between perhaps the vectors of different road users crossing each other, and that kind of situation going on. And then what we also developed is a simple reward function to assess the performance of this vehicle at different time steps, where we assigned a total penalty score, which was a combination of speed, acceleration, deceleration, and crash no crash criteria. And then we can implement certain fail thresholds for certain scenarios. And we try to create this at different time steps. Now, for example, in this first time step, the vehicle is going fine within the speed limits. It's not accelerating or decelerating in an untimely way, in a different way, and there is no crash, so there are no points accumulated. Now, going to time step 2, obviously I'm simplifying again. By time step 2, I'm jumping many seconds ahead, but again, this is just simplification to explain the concepts. Again, there is nothing that accumulates a point. And then what we see here is at time step 3, this gentleman jumps in front of the harsh deceleration zone. The vehicle starts decelerating, and immediately it starts accumulating penalty points for deceleration. But it doesn't go through the fail threshold, so maybe this is considered successful. Now, this is the simple one. Let's go to much more complex version of the case we showed earlier that we've been following throughout this presentation. Again, we start with no penalty points, and let's get cut to the chase, go to the interesting part. The pedestrian jumps in front of the red zone. Again, imagine this being not just like a box, but more like a vision cone. And at that point, immediately the vehicle starts decelerating and therefore starts accumulating a acceleration penalty score. And then the incident happens, the crash happens, and then another point is accumulated for crash, no crash. So then we are over our fail threshold for this incident. Now, the big question here is, who sets up the fail threshold and how should we set it up? Because if this incident was physically unavoidable, are we going to penalize this vehicle for something that it cannot physically avoid? That is surely not the point of this. So perhaps then what we should be doing is we should be comparing this behavior to maybe a human behavior. Like, is this vehicle going to perform in this incredibly challenging situation better than a human driver in a sober state, in this top peak condition could have done? If the vehicle can do that, perhaps that is already a benefit, and maybe we should look at that way to this thing. But actually, let's go back a step a little bit. Maybe what I've been saying all along was completely wrong way of thinking about this. Maybe the problem started long before this vehicle came to this position, because imagine this is smart mobility living lab. It's an urban environment. What you have in urban environments: cars parked, cars stopping, loading, unloading, EV charging points. So surely this vehicle, if it's going to operate in this design domain, it should be prepared for incidents like this. So what should have happened perhaps is this vehicle should have anticipated a potential risk behind this blind spot the moment it realized this is stopping there and there are traffic lights. So perhaps it should have slowed down way before it reached that point of no return. If that happened, what would have happened is then this box would have been much smaller and this person would have been in the orange zone. Yes, maybe it would have been a harsh deceleration, but it could have been avoided. So what I'm trying to say is, the other point we can look at this is, don't compare it to the human driver, compare it to what it could be, because if you're trying to achieve something much more ambitious than just replacing the current weaknesses of human behavior. So that's another way we can look at it. Obviously, there is a lot more work that needs to be done on this, but I hope this gives you the kind of things we looked at in this project, and we need to develop this further, and this facility surely will help us as we can combine scenarios that are experienced in the actual facility, and then we can do simulations of that, and we can explore these different concepts of what works, what doesn't work. And this will be an industry-wide push. Obviously, everyone will push different parts of it, but there are lots of benefits if you can achieve improvements in this area. So going back to the summary of this part, we start with the simulated scenarios, then we have the data coming from each run of the simulation, which we then fed into our reward function, which calculates some sort of cumulative score. And then what we're doing is, because we are doing XXX, I don't know, 1,000 iterations, let's say, we did for this case. By the way, I can already imagine people thinking how many iterations is good enough. That's another thing we can discuss, I guess, which I don't know the answer yet. I can tell you from the start. We do the X iterations, and then we end up with these results, which we can fed into our evaluation criteria. So before I finish, David, do you want to say something now, or should I go through the overview of what we talked? Which one would you prefer?
Actually, I think it might be a good spot to answer one of the questions that's come up. So Alexandros has put a question in saying, is the aim of this simulation to test the decision-making of the AI, or does it go further in identifying the corner cases of some of the sensing? Well, I think you could do both. I think for me, the interest is in assessing the behavior of the automated vehicle. So I guess that's aligned to the decision-making. And I think that example that you just gave, Jackie, was a perfect example of that. So in terms of the vehicle could decide, the behavior of the vehicle could be to slow down as it's approaching that bus, because that is clearly an increase in hazard. And it's then how you work that into a set of metrics that can be used to automatically evaluate thousands, potentially millions of automatically generated scenarios. I think that's the real challenge.
Yeah, I think as long as there is a centralized requirement, like some standardized requirement of how these are tested, this the exact methodology will be evolving over time, just like any other safety standard you have in other products. For me, the interesting capability here is, let's say you have a system that you develop and you want to test, and you want to maybe evaluate, would it be better if I write a system where this vehicle starts slowing down for every stopping vehicle, or is it better if I do some sort of different sensing system through like maybe a vehicle to infrastructure communication? If I invest on that, maybe we do 1,000 scenarios each, and then like do a high-level analysis, then you can go to detail analysis. This just gives you the playground to look into different things. Obviously, a lot more needs to be developed to fine-tune these things, but if nothing else, it gets us thinking in the right direction to bring in this experience to UK for future development. Going back to this project summary, just want to go through very quickly because I talked about different things. And last time we did this presentation, I had some questions which made me think actually I may not have been very clear in some parts. So let me go through again. So in this project, the main aim was to go from this point into that point and imagine how such a process could work in real life. And again, we decided to start with data available to us, which was stats 19, and then filtered it into a manageable size. And then we added extra information, enriched it with rates information, tapped into it to create some scenarios. And then we fed these into the simulation environment, which we brought in from the digital twin of SMLL. We also created some code to control the actor maneuver, through which we create these parameterized scenarios in these environments, which are run in the Carlo simulation in the state, through which you can connect a model, or you can use the sensors in the simulation for different things. You can even do vehicle to infrastructure communication simulation. And then we are simulating, for each simulation, we are recording some parameters from the simulation, some metrics, and then we are using these metrics in the reward function, which we can develop further, and then we are using these however many iterations deemed necessary into some sort of cumulative score. I guess maybe I should use the language. Sometimes I say we are doing this, we are doing that. Maybe I should all say we are envisaging some parts of this. Some parts of this we have actually done. Some of them are ongoing development for future. So I think that kind of summarizes what we have done so far and some of the things we've used. I'm now quitting this so I can actually see if this is still going on and everyone is here.
They are. There's a few questions. I think if people are prepared to stay on the line for another couple of minutes, we can probably answer these questions. So the one at the top there about V2X communications from smart traffic lights and whether the simulation would handle that. So I think you touched on that there, that's perfectly possible for that to be one of the input-output paths within the simulation.
Sorry, it's smart traffic lights. Yes, so basically, as I said, this is already something we're looking at the moment. We have a project called Service City, another Innovate UK project, where we are collaborating with Hitachi and Nissan. We are working on developing vehicle to infrastructure simulation in this platform at the moment. I'm sure you will hear more as we develop more of it. That's what I can say at this point of time, but definitely of focus.
Thank you. There's a few folks saying they would be interested in seeing more and asking if the model is available for academic research outside of SMLL. So I think the overarching response to both of those is if you could get in touch via the info@smartmobility.london email address that I put up earlier, or simplest thing is via the SMLL website. We are looking to collaborate. We've got lots of different mechanisms by which collaboration can happen. So yeah, please do get in touch with us, and very happy to talk further.
Actually, I can add to that. We are already talking to some organizations. I don't know, I can tell the names at the moment, and we are giving like, I know that we've given parts of the model to some organizations to see how we can collaborate, and that is also possible. Please, again, get in touch with SMLL. We want to use this as much as possible. Obviously, within the limits, it's not my own to say, yes, we can give it freely or anything like that, but definitely we are already collaborating with different partners from different parts of the industry to use it as much as possible.
Yeah, perfect. Thank you. And the last question that I think we haven't covered yet is from Andy. What was the view of DLG reliability for an incident in the real world? And I don't think I should comment on behalf of a major insurer. They insured the vehicle during the trial, so they insured each stage of the trial, and that was built on an evaluation of the safety case on a week-by-week basis. So as the trial developed and the testing incorporated more and more complex road features, that was a decision that was made again and again during the streetwise project, specifically for those trials. What their wider view is, I think it would be best to get in touch with them directly. Okay, thank you very much, everybody. I'll just scroll to the top, see if there's anything.
Chris asked something. How do we validate virtual results in the real world? How do we build confidence that the results in simulated scenarios are representative? This question came last time as well, David. And I think that question is something we all want to answer. The one thing I can say is the model we created was not done crudely. It was done to the highest standards of surveying, and with lots of fixed points, and the model was created at points to half a centimeter accuracy. So I guess I can turn the question around. What we're trying to say is we give you access to the physical site. We give you access to a model which was created painstakingly to a certain level of accuracy, and now it's up to you to access these things, work with us, and combine these things and see how we can use it for validation.
Indeed, and of course that's one of the key functions for the SMLL and the infrastructure that's built in there. So, for instance, there's an awful lot of sensing at many points around the network that gives you an external view on the behavior of the AV that can then be combined in and compared with the behavior in the simulation of the same situation. So you then get to use that information for validation. So I think that's pretty much everything. Is the certification ultimately saying the vehicles are fit for public roads? Is the only other thing I can see there. So, yeah, I mean that's part of the information I think that would be helping people to make that decision. So, as I mentioned previously, I think the overall certification of the vehicle would take place through existing channels with the United Nations and the type approval process. At UN or European level, but I think there's a really strong argument for a local certification, going back to those local driving norms, local rules of the road, and the fact that the many countries that are developing vehicles drive on the other side of the road to us, and it's not a given that a validation that is done driving on the right-hand side of the road will apply to driving on the left-hand side of the road. So I think it's perfectly reasonable to check all of those things with a subset of the testing that you would do for the full type approval. Okay, thank you very much, everybody, for your patience today. And we started a little bit late, and we're finishing a little bit late. So thank you very much for hanging in there. And we look forward to hearing from you via the SMLL website. Thank you.
Yeah, thank you very much. And I have to add, I've been sitting next to a very powerful computer which got really, really hot as I've been rendering these things live. So I'm sure glad that I can now open the window and have some fresh air. So.
Good. Thank you, Jackie.
Thank you very much for joining us, and feel free to get in touch if you have any ideas, any discussions, or any collaboration ideas. Please let us know. Happy to speak to you. All right.
Fantastic. Thank you, everybody.
Thank you and goodbye.
Cheers.